This is a double slit experiment. So we've got our laser and a double slit, believe it or not, and then our interference pattern of bright and dark spots or bands on the screen there. And I've used green light, they've given us the wavelength for that. Draw there, there we go. And describe the intensity at the exact centre of the interference pattern. Give a reason for this. So they're saying, is it a dark band or is it a bright band in the middle? Well, in the middle, it's a bright band. And, excuse me, they want a reason for that, and that reason is the path difference in the middle is 0. Okay, so what that means is if I put a ruler, say this was the middle one here, if I put a ruler from here to slit 1 and another ruler from here to slit 2, it would be the same distance. And so the difference in those two distances, or difference in those two paths, is 0 because they're the same. So the path difference in the middle is 0, and because of that, we have constructive interference occurring. Constructive interference occurs. Alright, the beam is now replaced with light of a lower frequency. The second dark band from the interference pattern would... So when you change the frequency, or you change the size of the slits, or you change the distance from the screen to the slits, what you end up doing is spreading them out or making them closer together. So we've just got to figure out which one of those is going to be spread out or closer together, these interference patterns. So light of a lower frequency. In my cheat sheet, I've got notes that tell me what happens if I change lambda. Right, and I know lambda equals C over F. So if the frequency goes down, if I divide by a smaller number, the wavelength goes up. So light of a lower frequency means increased wavelength. And on my cheat sheet, I've got increased wavelength means that the spots are spread out, or the bands spread out. Right, so which one talks about the second dark band spreading out from the middle? Does it become narrower? No. Does it remain in the same position? No. Does it move closer to the centre of the pattern? So that's the opposite of spreading out, that's becoming closer? No. It moves further away. There we go. So that's the band spreading out, as my second dark band is moving away. Right, there's that same picture again. The path difference from the slits to the second bright band of the interference pattern is, it's the second bright band. It's 1.4 by 10 to the 3 nanometers. It's going to be a path difference. Calculate the path difference from the slits to the first dark band from the centre of the pattern. So this isn't as easy as just saying, oh, I remember what the wavelength is, because I think in the first question the wavelength is 550, but because what's actually happened is they've used a new wavelength of a lower frequency and higher wavelength. That's what they said in B. So we can't use this, even though this says at the beginning one, we can't use this anymore. So we don't know what this new wavelength is, because this is a new question. Following from B. So we have to work out what the wavelength is from this guy here. So if this is the centre, that one there, it's the centre. We've got our first dark band, that's what we're going to end up finding. We've got our first bright, second bright band. And that has a path difference that we've got there. So the first bright band out has a path difference of 1 wavelength. The second bright band out has a path difference of 2 wavelengths. So we've got 2 wavelengths equals the second bright band out, the path difference, of 1.4 by 10 to the 3 nanometers. So then we get lambda equals, well, no, we'll just expand that out, equals 1400 nanometers. So if I rearrange lambda, I get 700 nanometers for lambda. And then the first dark bands, this is my first working. If I look at the dark bands on the top, center and first dark band is going to be a half wavelength. So this is my second point. The path difference to the dark equals a half lambda, and we now know what lambda is, 700, so that's 350 nanometers. I didn't even have to change anything into meters to do the calculation, but I do at the end because this is asked for it in meters. So 350 nanometers equals 350 by 10 to the minus 9. That's good enough. You could put it in as 3.5 by 10 to the minus 7, but they're both correct. By 10 to the minus 9 meters. Alright, a student reads on a website, the Young's experiment supports the particle model of light. Explain if this is correct or incorrect. Well, it's obviously incorrect, because Young's model supports the wave model. Incorrect. And what I'm going to do, whenever I do these, I explain what he saw in his experiment, and then how that explained by the wave model or the particle model. So what did he see in the experiment? We'll call it Young's experiment. Young's experiment there was an interference pattern of bright and dark bands, and this can't be explained by particle model. And I'm going to say what would be predicted if we had a particle model. If we had a particle model, they'd go through the two double slits, and you just get sort of two bright bands only would be predicted. And it is explained by the wave model. Through constructive and destructive interference. Sorry about the writing. When I look back on it, it's actually it's shocking. I'll see if I can fix it in the next one.